Hey there, ladies and gentlemen, boys and girls. Welcome back. Today we're going to talk a little bit about heat energy and what is heat and thermal energy. All right. Heat energy and thermal energy are kind of the same thing. And so we're going to kind of be using those words interchangeably here. I'm going to talk a little bit about is what is heat energy, what is temperature related to that, because a lot of people think heat and temperature are the same thing. They're close. They're close, but they're not quite the same thing scientifically. And then we'll talk a little bit about how heat energy transfers, because that's what a lot of what we're going to be talking about is one of the most common ways energy is transferred from one type to another. Normally has results in heat energy. And then we're going to talk about not only how it transfers, the ways it can transfer, and how certain materials transfer better than others. So a lot of this is about transferring of heat energy. So let's go ahead and get straight to it. All right. So first of all, what is heat energy? All right. Heat energy. All right. Heat energy has to do with molecule motion. All right. We talked about earlier that basically all types of energy are either some sort of potential energy or some sort of kinetic energy. And heat is a type of kinetic energy. And it's a type of kinetic energy that has to do at a very small level. It has to do with the overall particles, whether it's water or molecules or atoms of gold in a gold bar, or a copper and a copper wire. Or just the molecules of different types of molecules in my coffee. Right? They're all vibrating. All molecules are vibrating, and because all molecules are vibrating, they have they have kinetic energy, and that kinetic energy of molecules is called heat energy. All right. So I'm just going to abbreviate here. It's the kinetic energy of particles, or molecules, or atoms. I'm going to keep the vague term particles for right now. All right. And so right here we have, 4 different ones. And we talked a lot about this with solid, liquid, gas. This would probably be more like a solid, then a liquid, then a gas, right? And, this one has very low motion, and so low kinetic energy. And this one, or a gas, or a plasma, which would be even higher, has more kinetic energy, and thus a higher thermal energy. All right, so that's what heat energy is. All right, but now how we measure it is a little bit different. All right, and that's what when we start talking about like things like temperature. All right, so what we have here is we have, as we just talked about, heat. All right, so there's 2 ways to measure thermal energy. Heat is a measure of the total kinetic energy of the particles. So that is literally taking every single one of these dots and finding out or every one of these particles, right? And finding out how much kinetic energy every single one of them has and adding it up. Total kinetic energy. All right, we add them up. Obviously, the more molecules an object has, the more heat it has. Right? Even if these are all really small numbers, which we measure in joules again because it's energy, even if it's 0.1 joules, if you have trillions and trillions of atoms, that's a lot of heat. All right, even if each molecule is just moving a little bit. At the same time, you could take a smaller object like my coffee, right, where it's got a lot of heat energy because each particle is moving pretty quickly. All right, that kind of totaling up. All right, now that is different from, I'm going to put myself up here for a second. So we have heat energy, which is total energy, and we have it very confused with a lot of people think of thermal or temperature. All right, so temperature is a different measurement. And it's a little bit more of a valuable measurement when we're like using things day to day. It'd be hard to tell you like, oh, how hot's that? Is your coffee hot? How hot is it? It's like, oh, its heat energy, its heat is, 1,000 joules. Like that seems kind of a lot when because you're adding how many molecules there are. If I pour more coffee in there, there's more heat energy all of a sudden. So we actually do, we use temperature, which is actually the average kinetic energy of each molecule. So that's me taking that, or taking all of these, or adding up all of the molecules' kinetic energy, adding them up and dividing by how much mass there is, tells us the kinetic energy. It's about how much is each kinetic energy of each particle, which is a much more valuable measurement when we're talking about heat energy. So there's the difference. We have total energy, which is heat energy, and average kinetic energy of the particles. And we use temperature scales. We use Celsius is what we typically use in metric, but a lot of times, or in America and a few other countries, we use Fahrenheit. Actually, in science, we also use one called Kelvin. Kelvin scale has no negative numbers. It only goes down to 0. Where 0 is absolute 0, which is the absolute stopped motion, absolute 0 kinetic energy of particles, which is theoretically impossible to do. We've gotten very close in a lab setting. Even deep space has a little bit of heat. All right. Let's talk a little bit about how it transfers. All right. To that, I'm going to use a different tool. All right. So what I have here is I have 2 containers. All right. I have one that is very hot, and I have one that is very cold. Now, again, there's no such thing as cold. All right. So let me just rephrase that. Actually, let's go and change that. I have something that is very high thermal energy and something very low. All molecules are vibrating. We just interpret things that are cold as things that have low kinetic energy, which we'll talk about in a second. All right. And we have a bar that is connected between them. And we're going to talk about how energy transfers between 2 of these objects. All right. So we have a little copper bar that connects them. All right. We're going to talk about the transfer of kinetic energy. So as I hit play, you can see on the right there the bar of the temperature for each one. This is a lab we would have probably done in class, but sadness. All right. So we can see here that we started with the high energy and we started with the low energy, and they ended up kind of going into what we call equilibrium. They try to balance out. The one that, so the question is, what direction did the energy transfer? Well, the one with high energy got less energy. And where did that energy go? Energy can't be created or destroyed. It went to the one with low energy. It transferred along this copper into there. Energy, thermal, and all energy, especially thermal energy, which is one we use in a reference a lot, goes from high energy to low energy. So, for example, if you go outside and on a cold, go outside to the football stadium on those cold football nights in, late October, you go sit on the metal bleachers and it feels very cold. And it's not that it feels cold. All right. What's happening is your hand has higher kinetic energy than the metal bleachers. So when you put your hand on them, that energy goes from high to low. And it will transfer those bleachers. Those bleachers will get warmer after you sit on them for a while. But your butt or your hand will feel colder because it's got less energy. It's lost its thermal energy and it's given it to the bleacher. All right. So, there's ways that we can prevent that from happening, right? So we have energy that's always transferring from high to low. All right. Now, ways that we can prevent our butt from being cold is putting something in between there, right? Like a pillow or something, or some sort of cushion, right? That stops the heat going from your butt to the bleacher. All right. And that's what we call conductors and insulators. All right. We could put a conductor and an insulator. All right. These are all terms that you've probably heard before in science class. All right. So for example, all right, that was copper. That went pretty quickly. It took only about 300, but about 500 seconds for it to completely go to equilibrium. That was copper though. What if I chose steel? All right. So we still see the transfer of energy here. All right. But it's taking a lot longer to get there, longer than this time span is allowing to show there. I guess I can watch the temperatures on the left there and see how long it takes to do that. It's because the energy transfer is not very efficient. It's not doing it a very good job. All right, which this is better if you're trying to stop the transfer of energy. All right, this is copper is what we call a good conductor. It allows energy to travel very easily. Steel is not as good of a conductor. All right, we're slowly approaching that equilibrium. All right, compared to say something like glass, which is an extremely, extremely poor conductor. It's transferring, the temperatures are moving, but at an extremely low rate. This is one of the reasons why we use glasses for our windows, is because it doesn't let the heat inside the house into the house or outside the house, because it does allow it to transfer. All materials allow heat to travel through it. It's just some are way better than the others. All right. So let's switch back here. All right. So we basically have two kinds of things here. We have materials that allow the heat to travel very easily from one molecule to the next. All right, very easily, and it would be able to keep going. Right? These are what we call conductors. And then we have materials who are very poor conductors, all right, that do not allow that heat to transfer very well. They will transfer, but at very, very, very slow and inefficient rates. These are the opposite, or a bad conductor is also known as an insulator. So things like foam, glass, cotton, these are all really good insulators. They don't let energy transfer through them. Plastics, they don't let energy travel through them. So they're what they call an insulator. All right. And then there are some materials that are called, that are not very, they're kind of not, that are bad insulators, but not very good conductors either. They allow a little energy. And then over here, there would be even ones called superconductors that allow just crazy amounts of energy to travel through them with almost no resistance. All right, this brings us to our last topic here, is if we're going to be transferring energy from one place to another, whether through an insulator or a conductor, there are three ways that energy can travel. All right, there's conduction, convection, and radiation. All right, you know me and my silly phrases. Ready? Easy way to remember it. Conduction, convection, radiation. Conduction, convection, radiation. So let's talk about that. Conduction, all right? That's through direct contact. All right, energy is going to go from high to low. So in this case, if he's touching the hot pan, and let's say that's his hand, this is where that's where the high energy is. That's where the low energy is. The heat is going to transfer into his hand, and it's going to burn him. It's going to be ouchies. All right. So that's conduction. Conduction, direct contact, touching. Energy still goes from high to low. All right. If you have a liquid or a gas, you can get something called convection. All right. And this one we're very familiar with. It's just this idea that warm particles are going to, gotta switch it to that. Warmer particles are going to rise, and then when it cools down, it's going to sink. We see this in our houses all the time. If you have multiple layers in your house, like stories, I bet the coldest room in your house is typically your basement, and I bet your upstairs bedroom is typically warmer. And it's because in your house, the hot air, the high energy rises, and the lower energy sinks. All right. This is what we call a convection cycle. It's only in liquids and gases where one goes up, the higher energy goes up, lower energy goes down. All right, so that's conduction. Convection rises and sinks. And then the last one is radiation. Now, radiation is any energy. We already talked a little bit about this with electromagnetic radiation, talking about gamma rays and X-rays. And this is anything traveling through a space, not direct contact. Not direct contact, not a cycle. This is through a space. So if I put my hand over here, right, the heat energy is traveling and it's going to reach my hand, right? When you're trying to tell if something's hot, if a piece of metal is hot, you first test it by testing its radiation. You put your hand near it. You don't directly put your hand on it and do conduction because you might get burned real bad, right? Both in all of these situations, energy is going to travel from high to low, but we have conduction, convection, and then radiation through a space. All right. Again, you think it's goofy, but it works. All right, the hand signs. All right, so that's the 3 ways that heat can travel. They can travel in any direction. All right. And most of the time when you have a situation, you have multiple forms of heat traveling. Conduction, convection, and radiation, although some examples are better than others. My apologies. All right, well, that's it because I'm getting kind of long on this video. So those are that is what thermal energy is, how it transfers, and the methods of transfers: conduction, convection, radiation. All right, make sure you go back and add any of the vocabulary that you didn't add in case you accidentally just watched the whole video and didn't write anything in your handy dandy notebook. Otherwise, good luck, and may the science be with you.